In the realm of machine learning, determining the appropriate compute specifications for a training workload is crucial. This involves selecting the right hardware and software resources to ensure efficient and effective model training. The goal is to balance performance, cost, and scalability. This presentation will delve into the various aspects of compute specifications, including CPU versus GPU, memory requirements, storage options, and cloud versus on-premises solutions. By the end, you'll have a comprehensive understanding of how to tailor compute resources to your specific ML training needs. Training workloads in machine learning refer to the computational tasks involved in training a model. These tasks can vary significantly depending on the complexity of the model, the size of the dataset, and the specific algorithms used. For instance, deep learning models with millions of parameters require more computational power compared to simpler models. Understanding the nature of your training workload is the first step in determining the appropriate compute specifications. This involves analyzing the model architecture, dataset size, and training duration. Central processing units, CPUs, and graphics processing units, GPUs, are the primary hardware options for ML training. CPUs are versatile and can handle a wide range of tasks, making them suitable for simpler models and smaller datasets. GPUs, on the other hand, are designed for parallel processing, making them ideal for deep learning models and large datasets. GPUs can significantly speed up training times but are generally more expensive. The choice between CPU and GPU depends on the specific requirements of your training workload. Memory is a critical factor in ML training. Insufficient memory can lead to slow training times or even failure to train the model. The amount of memory required depends on the size of the dataset and the complexity of the model. For instance, deep learning models with large datasets may require several gigabytes or even terabytes of memory. It's essential to estimate the memory requirements accurately to avoid bottlenecks. Tools like memory profilers can help in assessing the memory needs of your training workload. Storage is another crucial aspect of compute specifications. Solid-state drives, SSDs, and hard disk drives, HDDs, are the two main types of storage. SSDs offer faster read-write speeds compared to HDDs, which can significantly reduce data loading times during training. However, SSDs are more expensive. The choice between SSD and HDD depends on the size of your dataset and your budget. For large datasets, a combination of SSD for frequently accessed data and HDD for archival storage can be a cost-effective solution. Choosing between cloud and on-premises solutions is a significant decision in determining compute specifications. Cloud solutions offer scalability, flexibility, and ease of use. They allow you to scale up or down based on your needs and pay only for what you use. On-premises solutions, on the other hand, offer more control and can be cost-effective in the long run for large-scale, continuous training workloads. The choice depends on factors like budget, data security, and the frequency of training workloads. Scalability is a key consideration when determining compute specifications. As your training workloads grow, your compute resources should be able to scale accordingly. Cloud solutions offer auto-scaling features that can automatically adjust resources based on demand. On-premises solutions may require manual scaling, which can be time-consuming and costly. It's essential to plan for scalability from the outset to ensure that your ML training can handle increasing data volumes and model complexities without performance degradation. Conducting a cost-benefit analysis is crucial in determining the appropriate compute specifications. This involves comparing the costs of different hardware and software options against the benefits they offer in terms of performance and scalability. For instance, while GPUs are more expensive than CPUs, they can significantly reduce training times, leading to faster time to market for your ML models. Similarly, while cloud solutions may have higher ongoing costs, they offer flexibility and scalability that can be beneficial in the long run. A thorough cost-benefit analysis helps in making informed decisions. Let's consider a case study of a deep learning model for image recognition. The model has millions of parameters and requires a large dataset for training. In this scenario, using GPUs would be more appropriate due to their parallel processing capabilities. The memory requirements would be substantial, necessitating several gigabytes of RAM. Given the large data set, SSDs would be preferred for faster data loading times. A cloud solution would offer the scalability needed to handle the extensive training workload, allowing for efficient resource management and cost control. Now, let's look at a case study of a simple regression model with a small dataset. In this case, CPUs would be sufficient for the training workload. The memory requirements would be minimal, and HDDs could be used for storage to keep costs low. An on-premises solution could be more cost-effective given the simplicity and infrequency of the training workload. This example illustrates how different training workloads require different compute specifications, emphasizing the importance of tailoring resources to specific needs. Monitoring and optimizing compute resources is essential for efficient ML training. Tools like TensorFlow Profiler, NVIDIA Nsight, and Azure Monitor can help track resource usage and identify bottlenecks. These tools provide insights into CPU, GPU utilization, memory usage, and data loading times, allowing you to make informed decisions about resource allocation. Optimization techniques, such as data parallelism and model parallelism, can further enhance performance. Regular monitoring and optimization ensure that your compute resources are used effectively, leading to faster and more cost-efficient training. To summarize, here are some best practices for determining compute specifications for ML training. 1. Understand your training workload by analyzing model complexity, dataset size, and training duration. 2. Choose between CPU and GPU based on the specific requirements of your workload. 3. Accurately estimate memory requirements to avoid bottlenecks. 4. Select appropriate storage options, balancing speed and cost. Decide between cloud and on-premises solutions based on scalability, budget, and data security needs. 6. Conduct a cost-benefit analysis to make informed decisions. 7. Use monitoring and optimization tools to ensure efficient resource usage. Determining the appropriate compute specifications for a training workload is a multifaceted process that involves careful consideration of various factors. By understanding your training workload, choosing the right hardware and software resources, and continuously monitoring and optimizing resource usage, you can ensure efficient and effective ML training. The next steps involve applying these principles to your specific ML projects, conducting thorough analyses, and making informed decisions to achieve the best possible outcomes. With the right compute specifications, you can accelerate your ML training and drive successful model deployments.